Welcome to The Explainer. Today we're diving into a paper that's, well, it's pretty mind-bending. What if, instead of just teaching an AI what to learn, you could teach it how to evolve its entire learning process?
So, let's kick things off with a question that really gets to the core of this whole thing. Why would you ever want to find just one best answer when you could find thousands of different high-quality answers? It's a huge shift in thinking.
And that question leads us straight to this really cool idea in AI called quality diversity. The whole point isn't just to find that one single champion, right? It's about building an entire collection of great solutions, each one good at something slightly different.
So formally, quality diversity, or QD, is all about generating this huge diverse collection of solutions that all perform really well. And I love this analogy. Instead of just climbing one mountain to find the absolute highest peak, what QD methods try to do is illuminate the entire landscape. They're trying to find all the possible peaks and valleys to map out everything that's possible.
Here's another way to think about it, and it's a great one. Imagine a master locksmith. They're not forging one single master key, no. They're creating a full key ring with a unique, perfect key for every single lock you could possibly imagine. And that's so powerful, right? Because it means you have the right tool ready to go no matter what situation pops up.
Okay, so how did we first try to do this? Well, the first big attempt to really nail this quality diversity thing was with an algorithm called MAP-Elites.
Now, MAP-Elites has this really elegant, simple approach. It takes the problem's entire behavior space, that's just a fancy term for all the possible ways a solution could behave, and it lays a grid over it. Then its only job is to try and find the absolute best solution it can for each and every little box in that grid. It just systematically fills out the map of what's possible.
Yeah, a really good way to picture this is an ice cube tray. You can think of each little compartment as a different type of solution you're trying to find. And MAP-Elites just goes along, trying to fill every single one of those compartments with the best possible ice cube, or solution, it can find for that specific type of behavior.
But there was a problem. This early explorer had a pretty big weakness. It relied on just random mutations to find new solutions. And look, that's fine for simple stuff, but it's super slow and inefficient when you're dealing with the massive, complex brains of modern AI. Neural networks with millions of connections. It's kind of like trying to write a masterpiece novel by just randomly hitting keys on the keyboard. You might get there eventually, but it's going to take a while. So, to fix that randomness problem, researchers had a clever idea. Let's combine MAP-Elites with the power of reinforcement learning, or RL. But what they ended up creating was this unstable alliance. It was powerful, for sure, but it came with a whole new set of problems.
And this really was a double-edged sword. On the one hand, you've got RL, which is state-of-the-art. It's way faster because it uses intelligent guided search. But on the other hand, RL brings its own baggage, It's incredibly sensitive to all its settings, what we call hyperparameters. The training can be super unstable, it's hard to scale up, and you often get locked into using just one specific RL algorithm. So powerful, yes, but also really brittle.
So, how do you get that power without all the instability? Well, this is where the paper we're talking about today comes in. Researchers at InstaDeep had a huge breakthrough. Their solution is called PBT-MAP-Elites. And the big idea is just brilliant. They decided to stop trying to evolve just a piece of the AI and instead evolve the entire agent.
And this is a really fundamental shift in thinking. See, before, methods were just focused on the AI's brain, its strategy, which is called the policy. This new approach evolves everything at once. It's kind of the difference between training just an athlete's technique versus training the athlete, their diet, their mindset, and their equipment all together as one cohesive system.
So, when we say agent in this context, what are we talking about? Well, it's basically three things. You've got the policy, that's the brain. Then you have other learnable bits, like the critic that helps it judge its own actions. And maybe most importantly, you have the hyperparameters, all those little tuning knobs that control how the agent learns in the first place.
The algorithm itself works in this really clever two-step loop that just repeats over and over. First, you have the population update. A whole group of these agents train together, and the best ones replace the worst ones, so the whole group just keeps getting stronger. Then you have the repertoire update. That's where these trained-up agents get added to our MAP-Elites grid, which is always looking for new and novel behaviors. So you have this constant push and pull, right? A balance between getting better at what you know and finding new things to do.
Okay, so the theory sounds great, it sounds amazing, but does it actually work? Well, the researchers put this new approach to the ultimate test in some ridiculously hard robotics challenges.
They use these environments called ant trap and humanoid trap. And the challenge sounds simple, but it's super deceptive. A robot is facing a trap. There's a little tempting reward right in the middle of it, but the real big prize is way on the other side. So the robot has to learn to ignore that immediate bait and find a clever way around. This is a classic test of exploration. It forces the AI to be smart, not just greedy.
And the results were just staggering. I mean, look at this. In the humanoid trap, which is notoriously difficult, PBT-MAP-Elites hit a fitness score of around 5,500. The other methods, they barely even got started. It was the only method that was actually able to solve this thing in the time they gave it. And this quote from the paper really puts that into perspective. They solved it in under 1 billion interactions with the environment. Other state-of-the-art methods that could eventually solve it, they needed tens of billions of interactions. That's not just a little better, that's a monumental leap forward in efficiency.
So, how on earth did it do it? What was the secret? Well, the secret weapon goes right back to that big idea: evolving the entire agent. The AI literally became a self-tuning machine, learning to tweak its own settings as it went. And what's really fascinating is how it adapted. When it was faced with that trap, the system figured out that the most successful agents were the ones that automatically cranked their exploration noise setting way up, like to high. All that extra randomness helped them break out of that obvious greedy path and actually discover a way around the trap. But here's the kicker. Once an agent found its way past the trap, it learned to do the complete opposite. It turned its exploration noise setting way down low. With less randomness, it could stop exploring all over the place and start perfecting its path to get the absolute highest score possible. It was dynamically changing its own learning strategy, depending on the challenge right in front of it. Incredible.
So, let's zoom out. What's the big takeaway from all this? Really, this new framework gives us the best of both worlds.
Look, this method is a real game changer for a few key reasons. It's flexible. You can plug it into pretty much any modern RL algorithm. It's robust because it learns its own best settings, which takes that huge, painful job of tuning away from the human researcher. It's built to scale up massively. And maybe most importantly, it builds this incredible bridge between two giant fields in AI, neuroevolution and reinforcement learning. It takes the stability and diversity of evolution and smashes it together with the raw speed and efficiency of RL.
It's just an incredibly powerful new tool for our AI toolkit. And it leaves us with one last big question to chew on. If an AI can evolve not just its strategy, but the very way it learns, what other incredibly complex problems in science and engineering and design are now, finally, within our reach?